All right, so all right, so what am I gonna make for the first one? What functional group will I get for my product? Hmm? Not a mean, not with an N. Amide. Hmm, amide. So you're gonna get an amide, and then am I gonna add it to carbonyl A or carbonyl B? A, right? Because the tert-butyl group blocks uh, B. B is big, so we'll make that amide. Next, we're going to get an ester, right? I think we have an example almost exactly like this from last lecture, but the stereochemistry here, just wanted to point out that we're not doing anything to the carbon-oxygen bond, so I will just end up with the ester, and I will keep the stereochemistry on that carbon-oxygen bond. And the last one, what am I going to do there? On where? No, it's supposed to be like that. I did not mess up super bad. This is the last thing we did on Friday. Transesterification, that's right. So you're going to swap the oxygen, or sorry, the alcohol part of one ester for another alcohol. So you're going to get rid of the sec-butyl that is on the ester, and you're just going to put an ethyl. Right? And you can do the transesterification under acidic conditions, which we have here, or we touched on it ever so briefly at the end of class. We did the mechanism. We can also do them under basic conditions, where you have, your ester and you have an alkoxide, and you can write then H plus, not always needed. Right? So if you do then H plus, you end up making an alcohol. If you write it where you don't have the then H plus, you still get the transesterification, but your byproduct is just going to be a new alkoxide. The then H plus is important if you're opening a lactone, right? So let's say you have actually make that a real lactone, a lactone. You need the acid to make sure that your product is an alcohol in the end. If you didn't have the then H plus, so when you get to, in this case, You can do this alkoxide with a sodium. I get to the O sodium. You don't want the O sodium, you want the alcohol. So you add the H plus to turn that into the alcohol. So that was transesterification. Next up on our reactions of esters, saponification. Saponification converts your ester into a carboxylic acid. You have an ester. You have hydroxide. This one you have to have the then H plus, and you will make a carboxylic acid, and you'll have your alcohol fragment that was on your ester. The metal here, again, is the big three: lithium, sodium, or potassium for the most part. Saponification kind of vaguely sounds like soapification, maybe, because this is how you make soap. You take animal fat, right, which biology people is just like a glycerin head unit attached to fatty acid chains. How are they attached? They're ester bonds, right? And then you add hydroxide, you break those, and then you get the soapy bit. And then you get soap. That's how you make soap, is you break up animal fat. If I learned anything from Fight Club, with enough soap, you can blow up anything. Right? Also, if you've ever touched sodium hydroxide or lithium hydroxide, they feel slippery. They're actually not slippery. What's happening is, as you touch the sodium hydroxide, they're actually saponifying the fats in your fingers, and you're turning yourself into soap. And so the hydroxide pellet feels slippery in your hand because you're becoming slippery, not it. So we can do this for we can do this for lactones as well. Same kind of deal, right? Where when you open the lactone, right, you're going to have your alcohol attached to the carboxylic acid. There you go. The mechanism is almost exactly the same as the basic transesterification mechanism. I should also point out, we only do saponifications under basic conditions. There's no acidic conditions for saponification. So I'll just pick a really simple one here. Pick like lithium hydroxide, then H plus. So we've got our lithium plus, hydroxide minus. We'll add our hydroxide to our carbonyl carbon, push electrons up. Right, same kind of deal where this can go back and forth. Right, sometimes we're going to push out that hydroxide. Sometimes we're going to push out the methoxide, but we use a large enough excess of hydroxide that we end up pushing the alkoxide out, right? And it can't go back. So sadly, this is not where the mechanism ends, even though I just made the carboxylic acid, right? Because what's in my reaction? I make this carboxylic acid, and there's a ton of hydroxide. I just made my lithium on there. I just made an alkoxide, right? So I keep making all of these bases around this carboxylic acid. So as soon as I make the acid, it's going to react with either the hydroxide that we have, more than likely the hydroxide. So we're going to have our hydroxide grab this hydrogen, put my lithium up here, and I'm going to end up making a lithium, in this case, carboxylate. Right? So as soon as I make the acid, it's going to react with the base that's in the reaction with it, and it's going to make a carboxylate. And now that's where the reaction is going to sit until we add acid, and then that's going to give us the carboxylic acid that we would isolate as the product. So you make the acid, but it's not stable under the reaction conditions, so it keeps reacting and becomes a carboxylate, which then gets protonated. Reasonable? That's not super hard, but it's just weird that you're like, I got the product. No, you don't. Two more steps, please. Then you have the product. So the first one is saponification. We make carboxylic acid. Now, as a byproduct, we do end up making the alcohol. For the most part, we're going to mainly be concerned with the carboxylic acid side of the ester when we do a saponification, but that's not always the case, right? You could have a really simple ester. You could have like just something simple like an acetate, and then like we'll call it some big important piece, right? And you're just trying to knock off the acetate, knock off the little ester that you might have used as a protecting group or something, and then care about the important part. But for us, for the most part, we're going to just be concerned about the acid side. Usually we're going to be knocking off like methanol, ethanol, propanol, and who cares, right? Next up, we're doing a transesterification under basic conditions. So we're just going to swap our alcohol fragment with a new oxygen. And then last one, transesterification under acidic conditions. Same thing. So far, these are all of our ester reactions thus far. Cool. Next step for ester reactions. So I can't really dress these up a whole lot, right? They're pretty, for the most part, they're pretty straightforward, right? So with a lactone, I'm going to break this carbon-oxygen bond, right? The ring is going to open where that carbonyl is, going to make an acid. And I'll have my alcohol. And again, to make sure I didn't screw up, 1, 2, 3, 4, 5, 6. 3, 4, 5, 6. Right, so the lactones are a little trickier. The acyclic esters are pretty straightforward, right? You're just going to chop off your oxygen or your alcohol fragment and just replace it with an OH. Everything on the acid side stays the same. You're just getting rid of that alcohol fragment, right? It makes an alcohol, but again, we don't care about it. Right, if I can buy bottles of isopropanol at Rite Aid, I definitely don't care about it. And then the last one, just don't forget, right? This is transesterification under basic conditions. You're just swapping one oxygen fragment or alcohol fragment for another. As far so good. We have the reduction of esters. So we have two possible products when we reduce an ester, and it depends on what reagents we use, right? So we can get primary alcohols, or we can make aldehydes, are our two options. Right, so again, I am concerned about the carboxylic acid side of the ester. So I'm talking about turning this carbon right here from being double bonded to an oxygen and bonded to another oxygen to just being a primary alcohol. Right, so I'm not really concerning myself with the alcohol side of the ester. I'm only worried about the acid side. So one way that you can get from a primary alcohol, you can get from an ester to a primary alcohol is to use lithium aluminum hydride. Just like we saw with acid chloride reductions, you need 2 hydrogens to get from the ester to the alcohol. And lithium aluminum hydride has 4 hydrides on it, so you just add that and you'll get from your ester to your alcohol. The other way that we can do this is if we use 2 equivalents of dibol, then H+. Remember that dibol only has 1 hydride on it, so I need 2 molecules of dibol to reduce 1 molecule of ester. Right, so I need 2 hydrogens. So if I need 2 hydrogens, I need 2 dibols because each dibol only brings 1 hydrogen. Fair? All right, so aldehyde is the product. You're going to have your ester. You have 1 equivalent of dibol at negative 78 degrees C. Then you're going to add H+, and this will make an aldehyde. So I think I've already told you guys, but just remember, negative 78 degrees C sounds like a very precise, very fancy temperature. Really, that's just the temperature you get when you throw acetone in with dry ice, right? Acetone is a solvent that there's probably the most of in any lab, and dry ice is easy to make. So it's more of like an oopsie that it's negative 78 all the time because it's the easiest cold bath to make. Right? But that being low temperature is important because if we made the aldehyde in the presence of the ester and the dibol, right? Aldehydes are more reactive than esters. So as soon as I made the aldehyde, it would react, right? What happens is because we do this at a cold temperature, kind of like how when we try to add an organolithium to a carboxylic acid, it gets stuck at the tetrahedral intermediate. This is doing the same thing. So when you add a hydride to your carbonyl carbon, you get your tetrahedral intermediate. and this is stable at minus 78 degrees C. So you add it, dieball has an aluminum as the metal that's carrying the hydride. So when you add it, you make this oxygen aluminum bond, right? O minus, aluminum is plus. And then you get this weak interaction between the aluminum and the oxygen of the ester. And that holds it together in this little four-membered ring that will not fall apart as long as you keep it cold, right? So as long as you keep the reaction cold, this doesn't fall apart. So I never make the aldehyde when there's any dieball around. The reaction gets stuck. When I then add my H plus, right? Right? This is going to kill any leftover dieball and protonate the oxygen. And then that lets it fall apart into the aldehyde. So I get my tetrahedral intermediate, it's stuck. I add the acid, it gets rid of any extra dieball, so there's never going to be any dieball when there's an aldehyde, and then protonates that oxygen, gets rid of the O aluminum, makes it an OH, and then that falls apart, kind of like the hydrate fell apart for the carboxylic acid reaction into the aldehyde. So as long as you keep it cold, it doesn't go anywhere. Again, this is not a topic we can like super dress up. So first one, right, we're just turning our ester into a primary alcohol. So everything on the carboxylic acid side comes along, and you make your alcohol. So for the next one, what am I going to get? What functional group am I going to spit out? I'm going to get an aldehyde. So all I'm going to do on a lactone is just break that carbon-oxygen bond, right? And I'm going to get my aldehyde. Right, so here, right, I drew it the same way the lactone looked, but if I would have drawn it like that, right, it's the same thing, right? You just have to be able to see, like, oh, okay, I see that I have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Right? So I might not draw it on like the exam as like an option the exact same way that the lactone looked. I might straighten out the chain to just be able to follow that and find it. And for the last one, what am I going to get? Going to get a primary alcohol. Same deal. We're going to break this carbon-oxygen bond. And we're going to get that. So last step is additions to esters with organometallics. Again, same kind of deal here. There are two possible products. Oops, tried to use actual letters. You can end up with a tertiary alcohol. Oops. This is kind of the most common product when you add an organometallic to an ester, and it's really easy to get. The other one is to get a ketone. Right, so this is rare. It's difficult to get to work. May not work. So in here, when we go over this, turning an ester into a ketone works on paper, works on your screen. We're good. In the lab, sometimes it works, sometimes it doesn't. So I'm giving you that caveat. Does that make sense? So when you see these conditions in this class, 100% it works. If I ever get you all to turn your backs on dirty biology and come to the cool team of organic chemistry, it works. I don't know, 50% of the time maybe. So that's just my little caveat. My like in the real world, boys and girls, that kind of thing. All right, so to get the tertiary alcohol, you have to have your ester. You need to add 2 equivalents of your organometallic. Usually it's a Grignard reagent. It can also be an organolithium. And you're going to add that organometallic twice to your carbonyl carbon. So this here, that carbon is that carbon right there. So it will work with an organolithium. Add 2 lithiums. Not 2 lithiums, add 2 isopropyls. Also works with lactones, right? Like all this stuff does. But again, it just gets a little harder sometimes to follow where everything's going to end up. We have 2 equivalents of our Grignard. And again, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I did not lose or gain any carbons there, so we're good, or any atoms, so we're good. Okay, so how does this work? What's the mechanism? Oops. What if I actually wrote real things? right? So we know the first part pretty well, right? We've got an ester, right? We've got a Grignard reagent. We know that our Grignard reagent is going to add to the carbonyl carbon. We're going to make a tetrahedral intermediate. Okay, now our tetrahedral intermediate wants to collapse and become a carbonyl again, right? Because having that C double bond O is much more stable. So these electrons are going to come down, push out the oxygen. I'm going to put it up here so I can write this beside it. So you make the ketone, and now you're making the ketone in the presence of your Grignard reagent. So as soon as you make this ketone, the next Grignard reagent reacts with the ketone. It ignores the ester because the ketone is more reactive. It's just easier to react with the ketone than it is to react with the ester, right? So you're going to have your Grignard reagent, add to your carbonyl carbon again. Then when you add your H+, you're going to protonate your oxygen. And get your tertiary alcohol. So since you're making a ketone here, you have to use up any ketone that you make before you get to react with your next ester. So that's why we need two equivalents, is to make sure we consume everything. But we make a tetrahedral intermediate, it collapses, we make something we can react with, and we react with that. So if we were to do this same reaction, but we only used one equivalent of Grignard. We'd end up with two products, right? We'd end up making the tertiary alcohol that we want, plus we would get the starting material back, right? And basically you'd get 50% of the tertiary alcohol and 50% of the ester. So let's think of kind of like the simplest example, which would be you've got 2 molecules of ester and you have 2 molecules of Grignard reagent. When the first Grignard reagent reacts with an ester, it makes a ketone, right? Now the second molecule of Grignard reagent has a choice. I can react with the ester or I can react with the ketone. The ketone's easier to react with, so it reacts with the ketone and makes a tertiary alcohol. Now you're all out of Grignard reagent and you still have the ester around, right? So that's what happens if you don't use two equivalents of Grignard reagent, is at the end, all of your Grignard reagent kind of went to making tertiary alcohol, and then you ran out before you react with all of your ester. That's why we need to have the excess, because that ketone is just way more reactive, and so we make it, it gets used. Fair? Now, how do we make the ketone? How can we just stop at the ketone? We're going to do the same thing that we did with the dibol. which is we're going to use 1 equivalent of Grignard at negative 78 degrees C in hopes of getting the reaction stuck at the tetrahedral intermediate, right? So we're going to add our Grignard reagent. Right, we're going to get something that is similar to the Dibol example. So this is the tetra, oops. And so this is hopefully stable at negative 78 degrees, right? So when it's the aluminum making this little four-membered ring, it's great. It's always stable at negative 78. Magnesium, it's a little more finicky. Depends on what the groups are, how big the groups are, what you've added, stuff like that. So that's why it's a little bit less consistent than the Dibol reaction, because it depends on how stable the tetrahedral intermediate is, right? How long it'll hang out. But again, for us, always works. It's great. So far, so good. All right. All right. So let's do A, B, and C first. Where do esters come from? So this whole set of slides we've been doing is about something derivatives. What is the something? What are all these functional groups we've been learning about? Where do they all come from? Carboxylic acid. So we can get esters from carboxylic acids. So it stands to reason that B needs to be a carboxylic acid. How can I turn a primary alcohol into a carboxylic acid? We did this last time. I got the same response. 3 ways to do this. One of them is purple, if that helps. It doesn't help, clearly. You could use KMNO4 or sodium dichromate, sulfuric acid, or chromium oxide water. Right? Any one of those 3 oxidants is going to take a primary alcohol and turn it into carboxylic acid. How do I turn a carboxylic acid into an ester? Many of you did it in lab last week or the last 2 weeks. I mean, a lot of it involves you just standing around for an hour. But you add the alcohol that you want to add, in this case ethanol, and then you add the sulfuric acid and heat. All right, so where do double bonds come from? So ways we learned how to make double bonds from Wittig reagents, so we don't have the right kind of starting material for that. But we can make them from alcohols, right? And so if we look at this double bond, right, you can say, okay, this carbon right here is this carbon. The carbonyl carbon looks like it's that carbon right there. Make sense? So you can say, okay, this green carbon could have been an alcohol, right? Because I know how to turn esters into alcohols. We just went over it, right? And I'm adding two identical groups, right? I'm adding two ethyls here. So I probably just have that, right? So I turned my ester into a tertiary alcohol. So I need two equivalents of my organometallic reagent to do that. That gives me my tertiary alcohol. And then how do I turn my tertiary alcohol into a double bond? We know three ways to do this as well. You could use POCl3 impurity. You could use H2SO4 in heat. You could use H3PO4 in heat. All got to do the same thing. Slightly, the first one and the last two, slightly different mechanisms, but still going to get you the same kind of place. So, what functional group is that? Maybe I should make it bigger. It is a cyclic acetal. Where do acetals come from? They come from, or cyclic acetals come from diols and carbonyls. So my diol part of this is the part attached to the six-membered ring. How can I turn a double bond into a diol? You could use cold dilute KMNO4, or you could use osmium tetroxide and hydrogen peroxide. And then this part right here would come from the carbonyl. So that is 3 carbons, the carbonyl in the middle, and acid to make the cyclic acetal. And with that, I'll see you next time.